Welcome to the Advanced Networking Demo Series. My name is Susan Wu. I'm in Outbound Product Management. We're talking about the Network Function Optimizer. With me, I have my colleague Deepak Michael. He's a network specialist and customer engineer in cloud networking. So what is the Network Function Optimizer? It's actually a product suite with advanced container networking features for the deployment and acceleration of network-intensive workloads. Network-intensive workloads could include AI/ML workloads that require high bandwidth and low latency running on GPUs. They could be containerized network functions, containerized firewalls, vRouters, VPN, proxies. They could be user plane functions in telco networks. So containers need additional capabilities to handle the network-intensive workloads. They require multiple interfaces. VMs can have up to 8 interfaces. Pods only have 1. They require advanced IP management. VMs can be assigned public and private IPs with persistence. Pods have ephemeral IPs. They require high performance. Features like DPTK. Default MTUs support VMs. Similar support would be needed for containers. Service steering. So service steering mechanisms and API definition would be needed for the pods. So the Network Function Optimizer can bridge this gap in 4 ways. Firstly, we provide multi-network pods, which enable multiple interfaces for pods and nodes in the GKE cluster. We provide a high-performance data plane, so we deliver a software-based high-performance data plane which removes the underlying hardware and NIC dependency. Thirdly, we provide the fast failover with persistent IPs, so we can map the application traffic to the public IP and use the same IP to initiate and receive traffic. Lastly, we provide Kubernetes-based, policy-based traffic steering, so you can steer the traffic to the container network functions using Kubernetes network policy. The benefits of using Network Function Optimizer are threefold. You get the multi-networking, getting the consistent interfaces for the network services. Secondly, you get the acceleration, so you can unlock the workload portability, allowing workloads to be scheduled to any pods without any dependency. Thirdly, you get agile network infrastructure, so you can achieve fast failover with the native integrations with public IP, bring your own IP, and network load balancers. We intend to upstream this work into the community, and we've been actively contributing to the SIG network. This actually leverages the native Linux acceleration to achieve the comparable performance. Also, we're leveraging the native Google Cloud to provide a cloud-native approach to networking. Now let me pass you to Deepak to see a walkthrough.
Thanks, Susan. Let's jump into NFO requirements. The first step in creating a multi-NIC pod is to create a GKE cluster and default node pool with a regular and secondary subnet. In addition, you would need to enable the flags, enable data plane v2, and enable multi-networking. Once deployed, create or use existing VPCs for subnet and IP address allocation for multi-NIC pods, and data communication to VPC workloads. Identify your multi-NIC requirements. Do you need a net device or L3 device type? Net device is used to communicate to GC instances in a VPC using a regular subnet range, while L3 device type utilizes the VPC secondary subnet range to communicate to GKE services or Docker containers running on GCE. When creating a multi-NIC node pool, you are required to deploy a machine type vCPU equal or greater than the number of VPCs in your deployment. As an example, in our deployment, there are 3 VPCs. Hence, we will configure a machine type with 4 vCPUs. Since the node pool prerequisites are satisfied, you can create an L3 and net device pod network. Lastly, deploy multi-NIC pods or deployments by leveraging the interface name annotation comprised of the Ethernet interface and network. Let's go over the demo architecture and validation use case. We have a Google Cloud project that contains a global VPC named Primary VPC with a GKE cluster deployed in US Central 1. The GKE cluster consists of the default node pool and network deployed with the flag enable data plane v2 and enable multi-networking. Within the project, we also have our net device and L3 VPCs. The multi-node pool is created by specifying the cluster, the net device VPC, L3 VPC, pod network, and machine type. In our first use case, we will perform a SSH into the net device pod and validate connectivity to the net device Apache instance in the net device VPC via EAP2 by performing a wget against the Apache server IP address. We will also perform a similar test, this time accessing the L3 Apache server in the L3 VPC via EAP1 validated by a wget. Let's take a look at our second use case. We will perform an SSH into the L3 network pod and validate connectivity to the L3 Apache instance in the L3 VPC via EAP1 by performing a wget against the L3 Apache server. That concludes the demo architecture. Time to jump into the deployment. Okay, let's jump into the demo deployment. First off, let's look at the VPC networks, the L3 VPC. We're going to look at the secondary subnet. This is the IP subnet range that the multi-NIC pod would take when deploying an L3 type interface. Now let's look at the net device VPC. And as the name suggests, this is the subnet that's going to be used when a net device interface is being utilized, which is also called a regular subnet range. Lastly, let's look at the primary VPC. This is where the default node pool will be deployed, and also your Ethernet 0 will pick up the IP address from the secondary range primary VPC subnet that's defined. Awesome. Now, looking at the firewall rules, we don't have any. We'll come back and we'll update the firewall rules later in the deployment. Okay, looking at CloudNet, we have CloudNet deployed in each one of the VPCs in US Central 1, utilized for internet egress. And taking a look at the compute engine, these are the GC instances running Apache server, L3 Apache, and net device Apache. They'll be used for our validation later in the deployment. We don't have any clusters deployed. As a prerequisite, we will need to deploy a new cluster for multi-NIC node pools, which we're going to go ahead and do right now. So opening up a Cloud Shell. And let's look at the flags, enable multi-NIC networking, and the enable data plane v2. These are the two required flags when creating a cluster. All right. Refresh. Okay, great. The cluster is up now. Let's take a look at the IP addresses used in the VPC. Great. It's the primary VPC, and it has the right IPs that we called out earlier. We can look at this from the nodes perspective as well. We got the default pool. Great. And just another breakdown of how this all works together. You can see the primary VPC is used for the network and the subnet, the primary node subnet, and then the pod IP address range. And that IP address will be used for Ethernet 0 when the pods are deployed. Okay, let's go ahead and create our multi-NIC node pool. Change the name to multi-NIC node pool. Everything else is fine here in terms of defaults. However, in the node section, we do need to change the machine type. Since we have 3 VPCs, we would need at least 3 vCPUs. Therefore, we're going to make a change to the number of vCPUs in this machine to 4. Yeah, awesome. Now under networking, this first section, this is for the default node pool. And yeah, the secondary range is in play. And you can see that because we specify the primary VPC Now the second section, this is for the L3 type device and the L3 VPC. We have a regular subnet. Now we also need to define the secondary subnet, right? So this is the subnet where the multi-NIC pod is going to pull an IP address. Lastly, we have the net device VPC, and it's going to use a regular subnet called net device subnet. Okay, we're good to go here. Security and metadata, everything is default, and let's go ahead and create the multi-NIC node pool. Awesome. So the multi-NIC node pool is now instantiated. Jump into it, and you could see the networking components. We have the primary VPC, the L3 VPC as well. Awesome. The secondary range is specified. And then we have the net device VPC. Okay, looking good. Okay, a network function optimizer. We have the default network, which is using their primary VPC. That's the default node pool, and it's also associated with the multi-NIC node pool. So keep that in mind. And we'll go ahead and jump into this, but I do want to look at the command line here at kubectl. Let's look at the networks. We only have one, the default network. In this section of the deployment, we're going to create the multi-pod network. We've met the prereqs. We've defined VPCs and associated subnets for the L3 device type and the net device. So let's specify the cluster in use. And the VPC that we're going to target here is the L3 VPC. And the network type, there's options, L3, DPDK, net device. This is going to be the L3 network. I remember for the L3 network, we need to find a secondary range, which we're doing here. Got it. Awesome. And we're going to define routes to the L3 Apache server, 172.16.20.0. Okay, awesome. So we see the network now. It's defined. Let's take a look here. Yep, it's you can see here in command line as well. Now, if we want to look into the details a little bit further, you can see the network definition. We have the routes that we specified, and then type is L3. Okay, looking good. Let's look at the GKE param set for the L3 network. Here you get a little bit more information as well. You can see the actual VPC in use, the L3 VPC, and the subnet. There's a lot of good information there to look at. And then again, you can look at that through the Cloud Console as well. Now let's go ahead and create the next one. Specify the cluster in use, the VPC network. This is going to be the net device VPC. Okay, got it. And the pod network type, we're going to use net device. And let's give it the name, net device VPC. Okay, great. Secondary range, if we don't need one, it's not required for a net device, remember? So that's only for the L3 type. Awesome. Let's go ahead and create our routes. And this route is going to be for the net device Apache. Okay, great. We got our 3 networks now. Let's take a deeper look into the configuration parameters. Describe on the network. Okay, looking at the network a little bit deeper. Yeah, we have the net device network. We have the routes, the 172.16.10.0. That's to the net device Apache subnet. And looking at the GKE param sets, I like looking at this one. There's more information here, which is useful. So yeah, it defines the VPC and the subnet. So awesome. So everything is mapped up accordingly. Let's go ahead and move on and create a pod. We'll go ahead and VI this pod, net device L3 pod YAML. Drop in the YAML configuration. We have the default interface, which is going to be Ethernet 0. That's going to be standard. Ethernet 0 is also your default network, Ethernet 1 L3 network, and Ethernet 2 the net device network. All right, so the pod's up and running. Taking a closer look at the YAML, we could obtain the IP addresses that are associated with the different networks. Again, the Ethernet 0 is default, Ethernet 1 is the L3, Ethernet 2 is the net device. But what I want to do is cross-reference the VPCs and look at the IP addresses a little bit deeper. All right, so L3, we got a 10.0.834. That lines up to the secondary IPv4 range. Now, let's take a look at the net device. That's using that regular subnet, so that's a 192.168.10.24, and that lines up to 10.0/24. Perfect. Ethernet 0 is going to pull an IP address 10.0.35. That's from the primary VPC, and that's the secondary range from that. Yeah, 10.0.0.0.21. Okay, awesome. Now, SSH into the pod, and we'll do an ifconfig, validate it once more, and everything lines up. At this point, let's look at the route table. So IP route, and we can see the routes that are being utilized for both Ethernet 2 and Ethernet 1. Awesome. So we picked up our next hops as well. So that looks correct, but we'll validate that later using a ping and a wget. So now we're going to create the L3 pod, same thing. So the Ethernet 0 is going to be the default interface. Ethernet 0 is also going to be defined by the network default Ethernet 1 with the network L3 network. Same type of BusyBox pod. So this looks good. Let's go ahead and deploy it. Go ahead and apply the config. Okay. Yeah, the pod's up and running. Look at the YAML file. Let's see what type of IPs we picked up. Yeah, so everything looks good here. Ethernet 0 default. The Ethernet 1 is going to be using the L3 network, so that lines up. And we picked up an IP address from the L3 network as well, the 10.0.87. Awesome. I do like cross-referencing the config. Now let's look at the L3 network. Yeah, 10.0.8.0.21. Awesome. And the Ethernet 0 interface 10.0.1.5, and that's from the primary VPC. Okay, so we'll only have two interfaces on this pod, Ethernet 0 and Ethernet 1. Okay, we'll SSH into the pod. Okay, everything lines up. Same config that we saw in the running config. And take a look at the IP route table. And we have the Ethernet 1. Okay, looks like everything is in order here. Okay, our pods are now validated. Let's go ahead and test connectivity. To do so, we need to create ingress firewall rules. The first one allows the net device subnet access to a net device Apache server. We will then create a firewall rule to allow the sec range L3 subnet access to the L3 Apache server. Remember, both of these subnets contain interfaces for the multi-NIC pod. Okay, so that's validated as well. Let's go ahead and get the IP addresses of the Apache server so we know what interface to reach. We got the L3 Apache, net device Apache. Okay, great. Got the internal IPs. Now let's go ahead and do some validation with the ping and the wget. The first one's from the net device L3 pod. Here we're going to go ahead and target the L3 Apache server, which is successful. And then we're going to target the net device Apache server, which is successful as well. Great. Let's go ahead and do a wget on the same server. So again, to the L3 Apache, that works. And let's go ahead and try this with the net device Apache server. And that's successful too. Awesome. So both Ethernet interface 1 and 2 are in use. All right, let's move to the L3 pod. And from the L3 pod, we're going to go ahead and try pinging the net device Apache server, and that won't work because we don't have an Ethernet interface that is linked to that network. So that failed. However, a ping to the L3 Apache server is successful. Okay, let's follow up with a wget. And this will work too because we have an Ethernet interface 1, which is connected. As a final validation step, let's leverage Logging Explorer to view logs obtained when we enabled ingress firewall rules logging. In the logging capture, we can see 2 entries, one per pod that contains a rich set of metadata consisting of pod IP address, in this case Ethernet 1, destination, node name pool, port, and protocol. As a best practice, it's recommended to enable firewall logging for troubleshooting and forensics. To learn more about Network Function Optimizer, please check out the code lab and documentation links in the description. Thank you for watching.